Imagine a quiet night, unlike any other. The sky above is calm. The stars shine with the same gentle light that has guided travelers, inspired dreamers, and comforted countless generations. Everything feels peaceful. Nothing seems out of place. Yet somewhere far beyond the reach of our eyes, a small piece of rock is silently traveling through space. It has no engines, no destination chosen by its own will. It simply follows the path carved by gravity. For millions, perhaps billions, of years, it drifts through the darkness without making a sound. No one watches it. No one notices it. It is only one among countless billions of asteroids wandering through our solar system. Most of them will never come close to Earth. Many will continue their endless journeys around the sun long after humanity is gone. But every so often, one of them crosses the path of a planet. And when that happens, entire worlds can change. It is easy to think of asteroids as intruders, as dangerous visitors arriving from the depths of space. But the truth is much more surprising. Long before they became potential threats, they were builders. To understand why, we have to travel back more than 4.5 billion years, back to a time before Earth existed, before oceans, before mountains, before life. Our solar system began not as a collection of planets, but as an enormous cloud of gas and microscopic dust drifting through the Milky Way. Perhaps a nearby exploding star disturbed that quiet cloud. Gravity slowly gathered its material together. The cloud began to collapse. As it did, it started spinning faster and faster. The center became hotter, denser, brighter. Eventually, that growing sphere ignited. Our sun was born. Around the young star, a wide, rotating disk of leftover material continued circling through space. Tiny grains of dust collided with one another. At first, they simply stuck together. Small became larger. Larger became larger still. Pebbles became rocks. Rocks became boulders. Boulders became enormous bodies, hundreds of kilometers across. The solar system was beginning to build itself. But construction is rarely gentle. Every growing world experienced countless collisions. Some impacts were small, others were unimaginably violent. Entire young planets smashed into one another. Fragments scattered across millions of kilometers. Some merged, others broke apart forever. The peaceful solar system we know today was born from extraordinary chaos. Among the countless objects left behind, many never became full-sized planets. Gravity from Jupiter continually disturbed their orbits. Instead of joining together, they remained separate. These ancient survivors became what we now call asteroids. In many ways, they are fossils from the birth of the solar system. Tiny time capsules, preserving materials that existed before Earth itself was fully formed. Some contain metals, others contain primitive rock. A few are rich in carbon compounds. Some even contain water locked inside their minerals. By studying asteroids, scientists are not simply examining space rocks. They are studying the ingredients from which our entire planetary neighborhood was assembled. Perhaps even more remarkable, Some researchers believe these wandering objects helped make Earth what it is today. When our planet was still young, its surface looked nothing like the peaceful blue world we know. Rivers did not flow. Forests did not exist. There were no oceans reflecting the sky. The young Earth was a hostile place. Molten rock covered much of its surface. Volcanoes erupted constantly. The atmosphere was thick with gases very different from the air we breathe today. Meanwhile, the solar system continued bombarding the young planet for hundreds of millions of years. Asteroids and comets repeatedly struck Earth's surface. Each impact released extraordinary amounts of energy. Many reshaped entire regions. Some excavated enormous basins. Others melted vast areas of crust. Yet, these impacts may also have delivered something precious: water. Although scientists continue investigating exactly how Earth's oceans formed, evidence suggests that water-rich asteroids likely contributed a significant portion of the water covering our planet today. If that is true, then every ocean, every river, every raindrop may carry a tiny piece of an ancient asteroid's history. The same may be true for some of the chemical ingredients necessary for life: carbon, nitrogen, complex organic molecules. These building blocks travel naturally through space. Some arrived here aboard ancient impacts billions of years ago. In a quiet and unexpected way, the rocks that once seemed like destroyers may also have become creators. Without those countless collisions, Earth might never have become the world we know today. Life itself may have required a little help from wandering stones drifting across the young solar system. But the story of asteroids does not end with creation. Hundreds of millions of years after life flourished across Earth, another asteroid forever changed the course of evolution. Around 66 million years ago, a rocky object, roughly 10 kilometers across, entered Earth's atmosphere at tremendous speed. Within moments, it struck what is now the Yucatan Peninsula in Mexico. The energy released exceeded billions of nuclear bombs. The impact excavated a crater nearly 200 kilometers wide. Shockwaves raced across continents. Wildfires spread. Dust and vapor filled the atmosphere. Sunlight faded. Temperatures changed dramatically. Food chains collapsed. Many species disappeared forever. Among them, the non-avian dinosaurs. For more than 160 million years, dinosaurs had dominated life on Earth. Then, in geological terms, everything changed almost instantly. Yet, from that catastrophe emerged new opportunities. Small mammals that had long lived in the shadows gradually expanded into newly available environments. Over millions of years, those mammals evolved into countless forms. Among them, eventually, us. It is a strange thought. Without that ancient asteroid, human beings might never have existed. The very event that ended one remarkable chapter of Earth's history opened another. Asteroids have always carried two possibilities: creation and destruction. They have delivered water, shaped continents, transported chemical ingredients, triggered mass extinctions, redirected the course of evolution itself. For billions of years, Earth simply accepted whatever the universe sent its way. Our planet had no choice, no warning, no defense, only chance. Every collision became another page in Earth's long history. But tonight, our journey asks a question, unlike any that came before. What if that is no longer true? What if, for the first time since Earth was born, one small species has developed the ability to see one of these ancient travelers coming, and perhaps to change its path before it changes ours? That possibility would have seemed impossible to every civilization that has ever lived. Yet today, it is no longer science fiction, because before we can protect our world, we first have to learn how to watch the sky. For most of human history, the sky was a place of mystery. People watched the sun rise each morning. They followed the changing phases of the moon. They learned the slow rhythm of the seasons by observing the stars. The heavens became a calendar, a compass, a source of myths, navigation, and inspiration. But they were also unpredictable. Every now and then, a brilliant comet would suddenly appear. A meteor would flash across the darkness. Something unexpected would happen above, reminding everyone that the sky was not as permanent as it seemed. For ancient civilizations, these events often carried symbolic meaning. Some believed they were messages from the gods. Others saw them as warnings of coming disasters. Few imagined that these mysterious lights were natural objects following precise paths through space. It would take centuries before humanity began to understand that the heavens obey the same physical laws as the earth beneath our feet. The invention of the telescope changed everything. For the first time, the distant lights overhead became places that could be studied rather than simply admired. Mountains appeared on the moon. The phases of Venus revealed that planets orbited the sun. Jupiter was found to have its own moons. The universe became larger and more understandable. Then, at the beginning of the 19th century, astronomers noticed something unusual. On the first day of January 1801, an Italian astronomer named Giuseppe Piazzi observed a tiny object moving slowly against the background of distant stars. At first, he believed he had discovered a new planet. Instead, he had found the first known asteroid. It would later receive the name Ceres. Soon, more objects were discovered: Pallas, Juno, Vesta. At first, each new discovery seemed extraordinary. But as telescopes improved, the number continued growing. Hundreds, then thousands. Today, we know of millions of asteroids orbiting the sun. Most remain safely confined to the asteroid belt between Mars and Jupiter. They quietly circle our star, largely undisturbed. But not all of them stay there forever. Gravity is constantly at work. A close encounter with Jupiter, a gentle pull from Mars. Even the tiny pressure produced by sunlight over millions of years can slowly alter an asteroid's path. Little by little, some begin drifting inward toward the inner solar system, toward the planets, including Earth. These objects receive a special name: near-Earth objects, often abbreviated as NEOs. The name can sound alarming, but it simply means their orbits bring them relatively close to our planet. Most never pose any danger. They pass millions of kilometers away. Some come even closer than the moon. Still, they continue safely onward. Only a very small fraction deserve careful attention. Finding them has become one of humanity's most important scientific efforts. Unlike earthquakes or volcanic eruptions, an asteroid does not suddenly appear without warning. If we discover it early enough, its future position can often be calculated years, sometimes decades, in advance. That possibility changes everything. Instead of waiting helplessly, we can prepare. Around the world, powerful telescopes scan the sky every clear night. They are not searching for beautiful photographs. They are searching for motion. A star remains fixed against the distant background. An asteroid slowly changes position. By comparing images taken minutes apart, computers identify tiny points of light that shift ever so slightly. Most discoveries today are made this way, not by chance, but through patient, systematic observation. Once an object is detected, the real work begins. Astronomers across different observatories quickly begin tracking it. Every new observation refines its orbit. Every additional night improves our understanding of where it will travel. Gravity allows remarkable precision. By applying the laws first described centuries ago by Isaac Newton, later refined through modern astronomy and computing, scientists can predict many asteroid orbits with astonishing accuracy. An asteroid millions of kilometers away may have its position forecast years into the future with incredible precision. Yet, there is always uncertainty, especially immediately after discovery. Imagine watching a distant airplane through a tiny window. At first, you know very little about where it is heading. After watching for several minutes, its path becomes clearer. Asteroid tracking works much the same way. The longer we observe, the better our predictions become. This process sometimes creates dramatic headlines. A newly discovered asteroid may initially appear to have a small chance of striking Earth. News spreads quickly. People become concerned. Then, after additional observations, the probability often drops to zero, not because the asteroid changed course, but because our measurements became more accurate. Science gradually replaces uncertainty with knowledge. This careful approach is one of the greatest strengths of modern astronomy. Scientists do not announce certainty before they possess sufficient evidence. Instead, every new observation improves the picture. Every calculation is updated. Every possibility is tested. It is a quiet process, patient, methodical, almost invisible to most people. Yet, every night, while much of the world sleeps, thousands of professionals and automated systems continue watching the heavens. The search has become increasingly sophisticated. Ground-based observatories work together across continents. Wide-field survey telescopes photograph enormous sections of the sky every evening. Advanced software automatically compares millions of stars and identifies anything that moves. Artificial intelligence increasingly assists by sorting enormous amounts of data far faster than any human observer could. Space-based observatories now join the effort as well. Operating above Earth's atmosphere, they can detect faint objects that are difficult to observe from the ground. Together, these instruments form something humanity has never possessed before: a planetary early warning system. It is still incomplete. Smaller asteroids remain difficult to detect. Objects approaching from the direction of the sun can remain hidden until they move into darker skies. Some still surprise us, but every year the system becomes better, more sensitive, more complete. There is an encouraging truth hidden inside all this work. The more asteroids we discover, the safer we become. At first glance, finding thousands of new near-Earth objects may sound frightening. In reality, it is exactly what astronomers hoped for. An asteroid cannot be tracked if it remains unknown. A known object is far less dangerous than an undiscovered one. Knowledge transforms uncertainty into preparation. Today, scientists have already identified the overwhelming majority of the largest near-Earth asteroids capable of causing global devastation. None of the known ones are expected to collide with Earth in the foreseeable future. That is reassuring. But the search continues, because smaller objects can still produce regional destruction, and because the solar system remains an active place. New objects are constantly being discovered. The work never truly ends. There is something quietly beautiful about this effort. For billions of years, Earth moved through space, unaware of what lay ahead. Now, for the first time in our planet's history, one of its species has begun watching the sky, not simply out of curiosity, but out of responsibility. Every telescope pointed upward represents an act of care. Every orbit calculated is another layer of protection. The heavens have not become less dangerous. We have simply become better at understanding them. And one day, perhaps sooner than anyone expects, that understanding may be tested. Imagine that one ordinary evening, among millions of familiar points of light, a telescope discovers something different, a tiny moving object, barely visible. At first, nothing seems unusual. Then the calculations begin. The orbit is refined, the observations multiply, and slowly a possibility emerges. This asteroid is not merely passing by. It may be heading directly toward Earth. For the first time, our quiet watch of the heavens becomes something far more urgent, because seeing a danger is only the beginning. The real question is what humanity would do next. Imagine waking up to a morning that feels completely ordinary. The sun rises on schedule. People leave for work. Children go to school. Airplanes cross the sky. Ships continue moving across the oceans. Somewhere, a telescope quietly begins another routine night of observation. Nothing appears unusual. The astronomers sitting inside the control room have performed the same task thousands of times before. The telescope slowly sweeps across the heavens. Image after image is collected. Millions of stars fill each photograph. Computers immediately begin comparing the new images with previous observations. Most of the moving objects are already familiar. Known asteroids, known comets, nothing unexpected. Then, a tiny point of light appears. It was not there before. Or rather, It has never been catalogued. The object is incredibly faint, barely distinguishable from the surrounding stars. At first, no one is alarmed. New asteroids are discovered all the time. This is simply another candidate awaiting confirmation. The discovery is automatically transmitted to astronomers around the world. Within hours, other observatories begin searching for the same object. One telescope finds it, then another. Soon, its existence is confirmed. A new asteroid has officially entered humanity's records. It receives a temporary designation, just another sequence of letters and numbers. Nothing about its name suggests that it might become one of the most closely watched objects in history. The first observations reveal very little. Astronomers know where the asteroid appears tonight. They know approximately how fast it moves across the sky, but they do not yet know its exact orbit. That requires patience. Every additional observation improves the calculations. Throughout the following days, the asteroid continues its silent journey around the Sun. Meanwhile, teams across different countries carefully refine its trajectory. Powerful computers simulate millions of possible paths. Tiny uncertainties remain. Perhaps it will pass safely by Earth. Perhaps it will miss by millions of kilometers. Or perhaps something else. The first orbital solutions appear. Most show a harmless flyby. A few suggest something more concerning. A very small possibility of impact. Perhaps one chance in 10,000. Scientifically, this is not unusual. Newly discovered asteroids often carry temporary impact probabilities until enough observations eliminate the uncertainty. The public rarely notices these early calculations. Astronomers do. They remain calm. No conclusions are drawn. More data is needed. Night after night, the asteroid is tracked. Each new measurement narrows the range of possible futures. The uncertainty slowly shrinks. Imagine watching a distant ship disappear into fog. At first, its destination is impossible to know. But as the fog clears, its course becomes unmistakable. The asteroid is much the same. Gravity has already determined its path. Humanity is simply learning to read it. Days become weeks. Weeks become months. Observatories across the world continue working together. Radar observations, when possible, provide even greater precision. The asteroid's position becomes clearer than ever before. Then, the calculations change. Not dramatically, only slightly, but enough. The impact probability increases, still very small, perhaps one chance in 1,000. Then, one chance in 100. No scientist panics. Science is careful. Extraordinary claims require extraordinary confidence. Every possibility is checked. Every observation is verified independently. Every equation is reviewed repeatedly. No announcement is made until the evidence demands it. Eventually, the uncertainty becomes too small to ignore. The asteroid's future path intersects Earth's orbit. Not approximately, not hypothetically, mathematically. There is now a significant possibility that both worlds will occupy the same place at the same time. For the first time, the conversation changes. This is no longer simply an astronomical discovery. It becomes an international concern. Scientific organizations begin coordinating immediately. Additional telescopes are assigned to continuous observation. Governments receive private briefings. Space agencies exchange data. Independent research groups verify every calculation. Nothing is hidden. Nothing is rushed. The entire scientific process depends upon accuracy. One incorrect conclusion could cause unnecessary fear. One overlooked detail could have unimaginable consequences. Weeks pass. The orbit becomes increasingly certain. Finally, the announcement is made. Carefully, calmly, without dramatic language, a press conference is held. Scientists explain what has been discovered. They emphasize what is known. Just as importantly, they explain what remains uncertain. The world listens. Many people hear the news for the first time. Some react with disbelief. Others become anxious. Many immediately imagine scenes from disaster movies. But reality is quieter, more methodical, more patient. The asteroid is still millions of kilometers away. Nothing visible has changed in the sky. Birds continue singing. Cities remain busy. The oceans continue rising and falling with the tides. Nature itself appears completely unaware. Only one thing has changed. Humanity now possesses knowledge about a possible future. That knowledge becomes our greatest advantage. Television programs discuss orbital mechanics. Newspapers explain impact probabilities. Teachers answer students' questions. Families gather around dinner tables, talking about something no previous generation ever imagined discussing. Not because the asteroid has arrived, but because it has been seen. For the first time, people begin to understand the extraordinary value of time. If an asteroid were discovered only days before impact, very little could be done. Months would help. Years would help far more. Decades could completely transform the situation. In planetary defense, time is not simply important. It is everything. Every additional year allows more careful planning, more precise missions, greater confidence. The difference between disaster and success may depend not upon technology, but upon how early the object was discovered. This realization quietly changes the way humanity views the night sky. Astronomy is no longer only about understanding distant galaxies. It is also about protecting home. Eventually, after months of continuous observations, the calculations reach an extraordinary level of confidence. The asteroid will strike Earth unless something changes its course. The probability is no longer 1% or 10%. It approaches certainty. The question that now confronts humanity is unlike anything faced before. Not whether the asteroid exists, not whether it is dangerous, but whether we possess the ability to stop it. For billions of years, every asteroid followed gravity alone. No planet ever resisted. No world ever fought back. But today, one small civilization begins asking an entirely new question. Can intelligence alter the path of the heavens themselves? The answer may be one of the greatest achievements our species has ever attempted. For most of Earth's history, an asteroid on a collision course meant only one thing: Impact. Gravity decided the outcome. The planet simply waited. There was no warning, no preparation, no possibility of changing what was about to happen. But now, for the first time in more than 4 billion years, one species has begun asking a remarkable question. Could we change the future? At first, the answer might seem obvious. Many people imagine the same solution. If an asteroid is heading toward Earth, why not simply destroy it? It is an understandable thought. After all, that is how many stories portray the problem. A powerful explosion, a dramatic rescue, the asteroid shattered into harmless pieces, humanity saved. It is an exciting image. But reality is much more complicated. Imagine throwing a large rock through a window. Now imagine throwing 1,000 smaller rocks instead. The total amount of material remains almost the same, only its shape has changed. If a dangerous asteroid were broken apart without careful planning, its fragments could continue traveling toward Earth. Instead of facing one large impact, we might face many. Some pieces could burn up harmlessly. Others could still strike the surface. In some situations, fragmenting the asteroid might actually make the problem worse. This is why planetary defense scientists rarely speak about destroying asteroids. Instead, they speak about something far more elegant: changing their path. The remarkable thing about objects moving through space is that they usually travel for millions of years without encountering anything. Their orbits are incredibly predictable, and because they are so predictable, even an extremely small change made far enough in advance can completely transform where the asteroid will be years later. Imagine placing your finger gently against the side of a moving bicycle. You do not need to stop it. You do not need to lift it into the air. A tiny change in direction, applied early, can cause it to arrive at a completely different place much farther down the road. Asteroids behave in much the same way. The goal is not to overpower them. The goal is simply to persuade them to miss, perhaps by only a few hundred meters or a few kilometers. From Earth's perspective, that tiny difference becomes the difference between catastrophe and a harmless flyby. This idea led scientists to develop one of the simplest and most practical planetary defense strategies ever proposed: the kinetic impactor. Its name sounds technical. Its principle is surprisingly straightforward. Instead of carrying enormous explosives, a spacecraft simply collides with the asteroid at very high speed. The spacecraft sacrifices itself. Its momentum is transferred into the asteroid. The change in velocity is incredibly small, sometimes only a fraction of a millimeter per second. Yet, if this tiny adjustment happens years before the predicted impact, the asteroid gradually drifts onto a different path. A tiny push, a massive result. For decades, this idea remained purely theoretical. Scientists were confident it would work. But confidence is not the same as proof. Eventually, humanity decided to test it. In early RE, NASA launched a spacecraft with a single purpose: not to explore a planet, not to study a comet, but to deliberately crash into an asteroid. The mission became known as DART, the Double Asteroid Redirection Test. Its destination was not a dangerous asteroid threatening Earth. Instead, it targeted a safe system located millions of kilometers away. A larger asteroid named Didymos, accompanied by a much smaller moonlet called Dimorphos. Dimorphos was chosen carefully because changing its orbit would pose absolutely no danger to Earth. It offered the perfect natural laboratory. For months, the spacecraft quietly crossed interplanetary space. Its journey lasted nearly a year. Then, on September 26, 2022, after traveling more than 11 million kilometers, DART reached its target. The final images sent back to Earth were extraordinary. Dimorphos slowly grew larger and larger in the camera's view. A rough, rocky world, silent, unaware that it was about to become part of history. Then, the transmission ended. The spacecraft struck the asteroid at more than 22,000 kilometers per hour. For a brief moment, humanity intentionally altered the motion of a celestial object. The impact itself was only the beginning. Astronomers around the world immediately began measuring Dimorphos's orbit around Didymos. Would the collision actually change its motion? The answer arrived sooner than many expected. Yes, the orbit had changed. Even better, the effect was larger than scientists had predicted. Material blasted away from the asteroid acted almost like the exhaust from a rocket. The ejected debris produced additional momentum, giving the asteroid an even greater push. The experiment was an extraordinary success. For the first time in history, human beings had demonstrated that an asteroid's orbit could be changed intentionally. The importance of that achievement is difficult to overstate. DART did not save Earth from an incoming impact. It accomplished something even more important. It transformed an idea into a proven capability. Until then, planetary defense had existed largely on paper. Now, it had entered reality. Of course, many questions remain. Every asteroid is different. Some are solid rock. Others resemble loose collections of boulders held together only by weak gravity. Some rotate rapidly. Others spin slowly. Some contain large amounts of metal. Others are rich in carbon-rich material. The same strategy may not work equally well for every object. That is why future missions are so important. Scientists continue studying asteroids in remarkable detail. Spacecraft visit them, land on them, collect samples from their surfaces. Every new mission teaches us something valuable, not only about the history of the solar system, but about how we might someday protect our own world. There is something quietly profound about this moment in history. For billions of years, gravity alone shaped the destinies of planets and asteroids. Now, a tiny civilization living on one small world has learned to make an object in space arrive somewhere different than gravity alone intended. It is an incredibly modest achievement on the scale of the universe. The orbit changed only slightly. The asteroid itself was small. Yet, symbolically, it represents something extraordinary. For the first time, Earth is no longer entirely passive. Our planet now possesses inhabitants capable of influencing events beyond its own atmosphere, not through force, but through understanding, through careful observation, through physics, through patience. Perhaps that is the greatest lesson DART offered. The universe does not always require enormous actions. Sometimes, changing the future begins with the gentlest possible push. But the kinetic impactor is only one idea. Scientists have imagined several others, some even stranger, some slower, some far more ambitious. Because every asteroid is unique, humanity may someday need an entire collection of tools, and each one tells another chapter in the remarkable story of learning not merely to survive the universe, but to gently shape our place within it. The success of the DART mission answered an important question. Yes, humanity can change the orbit of an asteroid, but it also revealed another truth. There is no universal solution. Every asteroid is different. Some are small enough that a gentle push may be all they require. Others are enormous. Some rotate quickly. Others tumble unpredictably through space. Some appear to be solid rock. Others resemble loose piles of rubble, barely held together by their own gravity. If one dangerous asteroid were discovered tomorrow, scientists would not immediately choose a single plan. Their first task would be understanding the object itself, its size, its shape, its composition, its rotation, its internal structure. Only then could the best strategy be chosen. This careful approach reflects one of science's greatest strengths. Rather than searching for one perfect answer, it prepares many possible answers, each designed for a different situation. One of the most elegant ideas ever proposed does not involve striking the asteroid at all. Instead, it relies on one of the weakest forces imaginable: gravity itself. This concept is known as the gravitational tractor. Imagine placing a spacecraft beside an asteroid, not landing on it, not touching it, simply hovering nearby. Both objects possess mass, and every object with mass attracts every other object through gravity. Normally, the spacecraft would be far too small for this attraction to matter. But space is patient. If the spacecraft remained beside the asteroid for months, or even years, its tiny gravitational pull would slowly tug the asteroid toward it. The effect would be almost unimaginably small, far weaker than the weight of a single sheet of paper resting in your hand. Yet over enormous stretches of time, even such a gentle force could gradually alter the asteroid's orbit. The spacecraft would constantly fire small thrusters to maintain its position, never pushing directly against the asteroid, only allowing gravity to perform its quiet work. There is something beautiful about the idea. No explosion, no collision, no dramatic impact, only patience. A silent spacecraft gently persuading an ancient rock to follow a slightly different path through the solar system. The challenge, of course, is time. A gravitational tractor works only if we discover the asteroid many years before any possible collision. Fortunately, planetary defense has always favored early action. The sooner we detect a threat, the more options become available. Another fascinating possibility involves landing directly on the asteroid, instead of pushing it from the outside. A spacecraft could become part of the asteroid itself. Imagine powerful engines carefully anchored to its surface. Day after day, month after month, the engines fire, not with enormous force, but continuously. Little by little, the asteroid's orbit begins changing. This strategy sounds simple, yet landing on an asteroid is surprisingly difficult. Many asteroids possess extremely weak gravity. Some rotate rapidly, others have rough, unpredictable surfaces covered with loose rocks and dust. Anchoring heavy machinery securely could become a major engineering challenge. Still, humanity has already demonstrated that landing on asteroids is possible. Spacecraft from several countries have successfully visited these ancient worlds. Some have even collected samples and returned them safely to Earth. Each mission teaches valuable lessons, not only about asteroid science, but about future planetary defense. There are other ideas as well. Some involve sunlight itself. Although sunlight feels gentle on Earth, photons carry momentum. When light strikes an object, it exerts an incredibly tiny force. Normally, this effect is almost impossible to notice. Yet, over years, it slowly changes the motion of small asteroids. Scientists already observe this natural process. It is known as the Yarkovsky effect. As an asteroid absorbs sunlight and later radiates heat back into space, the escaping infrared energy acts like an almost invisible thruster. The force is extraordinarily weak, but given enough time, it can gradually shift an asteroid's orbit. Some researchers have wondered whether this natural process could be enhanced, perhaps by changing the asteroid's surface, painting part of it a different color, covering sections with reflective material, or using mirrors to concentrate sunlight. The goal would not be speed, only a tiny, continuous change accumulating over many years. Again, patience becomes the most powerful tool. Then there is the option that receives the most attention in popular culture: nuclear explosions. Movies often portray enormous bombs destroying incoming asteroids moments before impact. Reality is far more restrained. Scientists generally view nuclear devices as a last resort, not because the physics cannot work, but because the risks are significant. Detonating a nuclear device directly inside an asteroid could fragment it into many pieces. If those fragments continue toward Earth, the situation might become even more dangerous. Instead, modern studies often consider detonating a nuclear device at a short distance from the asteroid. The intense burst of radiation would rapidly heat one side of the surface. Material would vaporize. That expanding cloud of gas would act like rocket exhaust. The asteroid would receive a small push without necessarily breaking apart. It is a subtle difference. The objective remains the same. Do not destroy the asteroid. Simply change its path. Even this approach depends heavily upon understanding the asteroid beforehand. A dense metallic asteroid behaves differently from a porous, carbon-rich one. A solid, monolithic rock responds differently from a loose rubble pile. Composition changes everything. Imagine trying to move a bowling ball. Now, imagine trying to move a pile of loose sand with the same technique. The results would be completely different. Asteroids present the same challenge. From a distance, two objects may appear almost identical. Up close, their internal structures may have almost nothing in common. That is why planetary science has become such an important field. Every spacecraft sent to study an asteroid improves our future ability to defend Earth. Every sample returned to laboratories reveals new details. Every observation reduces uncertainty. Knowledge itself becomes part of our planetary defense system. There is another remarkable lesson hidden within all these strategies. None of them rely on extraordinary luck. None require impossible technology. Most depend upon physics we already understand remarkably well. Gravity, momentum, light, heat, orbital mechanics. The challenge is not discovering magical solutions. It is applying familiar laws of nature with extraordinary precision. This realization is quietly inspiring. For centuries, humanity imagined surviving cosmic disasters through strength. But reality suggests something different. The future may depend less upon power and more upon understanding, less upon violence and more upon patience, less upon heroic last-minute rescues, and more upon careful preparation, decades in advance. Yet even the finest technology possesses limits. Every strategy we have explored tonight depends upon one precious resource: time. Without enough warning, even our greatest achievements may not be enough. And that raises one final, difficult question. What happens if we discover the asteroid too late? What if the universe gives us only months or weeks instead of decades? At that point, the greatest challenge may no longer be changing the asteroid. It may be preparing ourselves. Throughout our journey, one idea has quietly appeared again and again. Time. Not technology, not powerful rockets, not advanced computers. Time. Every strategy we have explored depends upon discovering an asteroid early enough to act. A tiny change made decades in advance can completely prevent a collision. The very same change made a few weeks before impact would accomplish almost nothing. Space is patient. Orbital mechanics reward those who prepare early. But what if the universe offers no such opportunity? What if one ordinary night, an observatory discovers an asteroid that has remained hidden until the very last moment? At first, this may sound unlikely. After all, we now monitor the skies more carefully than ever before. Thousands of near-Earth objects have already been catalogued. Powerful telescopes scan the heavens every clear night. Space-based observatories continue expanding our reach. Yet the solar system is vast. Not every asteroid is easy to find. Some approach Earth from the direction of the sun. From our perspective, their faint light is lost in the overwhelming brightness of daylight. Ground-based telescopes simply cannot observe them. Others are very small, dark, barely reflecting sunlight. They remain almost invisible until they come remarkably close. Most of these objects are not large enough to threaten civilization, but they remind us of an important truth. Detection is never perfect. Imagine an asteroid discovered only 6 months before impact. The calculations are confirmed. The trajectory is certain. There is no longer any doubt. Would humanity still have enough time? The answer depends on many things. The asteroid's size, its speed, its composition, the launch opportunities available, even the positions of Earth and the asteroid in their respective orbits. Sometimes, 6 months may simply not be enough to launch a successful interception mission. Building a spacecraft takes time. Testing it takes time. Launching it depends upon weather, engineering, and orbital alignment. Even after launch, the spacecraft still has to reach its target. Every passing day reduces the available options. Now imagine the warning arrives only a few weeks before impact. At that point, planetary defense changes completely. The focus is no longer preventing the collision. It becomes protecting people. Scientists would continue refining the impact prediction, not because the collision could still be prevented, but because every improvement helps identify where the asteroid is most likely to strike. Even a small change in the estimated impact location could influence millions of lives. Modern orbital calculations are astonishingly precise. As additional observations arrive, the uncertainty continues shrinking. Eventually, scientists could identify the expected impact region with remarkable accuracy. Only then would another enormous challenge begin: evacuation. Moving a single city before a major hurricane is already an extraordinary logistical effort. Imagine relocating millions of people away from an impact zone. Roads, railways, airports, medical services, food supplies, communication systems. Everything would need careful coordination. The challenge would not belong to one country alone. It would become an international effort. Fortunately, not every asteroid poses the same level of danger. A smaller object may explode high in the atmosphere. A larger one might survive long enough to create a regional disaster. Only the largest asteroids, those measuring several kilometers across, carry the potential for global consequences. Fortunately, scientists believe nearly all known asteroids of that size have already been discovered. None are expected to strike Earth in the foreseeable future. That knowledge offers genuine reassurance. Still, regional impacts remain possible. History reminds us of this. In Bai, a relatively small object exploded above Siberia near the Tunguska River. The blast flattened millions of trees across more than 2,000 square kilometers. Remarkably, no large impact crater was formed. The object most likely disintegrated in the atmosphere before reaching the ground. Even without a direct impact, the energy released was enormous. More recently, in Arli Sen, another asteroid entered Earth's atmosphere above the Russian city of Chelyabinsk. Only about 20 meters across, it exploded high overhead. The shockwave shattered thousands of windows. More than 1,000 people were injured, mostly by flying glass. The event served as a powerful reminder. Even relatively small asteroids deserve attention. Fortunately, Chelyabinsk also demonstrated another important fact. Earth's atmosphere protects us remarkably well. Every day, tiny pieces of cosmic debris burn harmlessly overhead. Most never reach the surface. Only the largest survive their fiery descent. Even so, preparedness remains essential. If an impact could not be prevented, emergency planning would become humanity's greatest tool. Governments, scientists, engineers, emergency responders, military organizations, medical teams, international agencies, all would need to cooperate in ways rarely seen before. Planetary defense would no longer be a scientific challenge alone. It would become a human one. Perhaps this is the most profound lesson hidden inside the entire subject. The asteroid would not care about national borders. It would not distinguish languages, religions, cultures, or political systems. From the perspective of space, Earth is one planet. Its inhabitants share the same sky, the same atmosphere, the same future. Sometimes, it takes a cosmic perspective to remind us of something surprisingly simple. Humanity has always lived together on one remarkably small world. The universe has never recognized the lines we draw across maps. An approaching asteroid would make that reality impossible to ignore. Every successful response would depend upon cooperation, information shared openly, resources combined, knowledge exchanged freely. No single observatory could monitor the entire sky. No single nation could solve every challenge alone. Planetary defense has always been international, by necessity. Astronomers across dozens of countries already collaborate every night. Data moves across the globe almost instantly. Discoveries belong to everyone. Perhaps this quiet cooperation represents one of humanity's greatest strengths. Long before any asteroid threatens Earth, people from every continent are already working together to ensure that if such a day ever comes, we will not face it alone. There is something deeply hopeful about that. For billions of years, Earth endured whatever the universe delivered. Now, its inhabitants prepare together, not because disaster is inevitable, but because preparation itself is an act of wisdom. And every year, that preparation improves. New telescopes, more powerful computers, better spacecraft, smarter detection systems. Future generations may inherit something extraordinary. Not merely the ability to predict an impact, but the ability to prevent one almost routinely. Perhaps the greatest chapter in planetary defense has not yet been written. Perhaps it is only beginning. Because the future of protecting Earth may look even more remarkable than anything we have imagined so far. For most of Earth's history, the future arrived without warning. A volcanic eruption, a changing climate, an asteroid emerging from the darkness. The planet simply endured whatever the universe delivered. But something remarkable has begun to change. For the first time, a species is not merely reacting to the future, it is trying to see it before it arrives. Every year, the network watching the sky grows larger. More telescopes, more observatories, more countries working together, more eyes quietly scanning the darkness. The goal is wonderfully simple. Find tomorrow's dangers today. The earlier an asteroid is discovered, the gentler the solution can be. A tiny adjustment made decades in advance may prevent an event that would otherwise reshape history. That is why the future of planetary defense begins not with rockets, but with discovery. Some of the most important observatories of the coming decades may never leave Earth. Powerful survey telescopes will photograph enormous portions of the sky every few nights, night after night, year after year, building an ever more complete map of the countless objects moving through our solar system. Each new observation reduces uncertainty. Each newly discovered asteroid transforms an unknown risk into a known object that can be studied. Knowledge itself becomes our first line of defense. At the same time, space-based telescopes are opening entirely new possibilities. Unlike observatories on Earth, they are not limited by clouds or daylight or the atmosphere. Some future missions will observe from positions where they can detect asteroids approaching from directions that remain difficult to monitor from Earth's surface. Objects once capable of hiding in the sun's glare may become visible years earlier. That additional warning could make all the difference. The future is also likely to belong increasingly to artificial intelligence. Every night, modern telescopes collect extraordinary amounts of information, far more than any team of astronomers could examine manually. Machine learning systems are becoming increasingly skilled at recognizing moving objects, identifying unusual trajectories, and filtering millions of observations into manageable discoveries. Artificial intelligence will not replace astronomers. Instead, it will become another patient assistant, working continuously, never tiring, helping scientists focus their attention where it matters most. There is something fitting about this partnership. Human curiosity combined with machine precision, together watching over one small planet. Future planetary defense may extend far beyond simply discovering dangerous objects. Imagine spacecraft permanently stationed in space, not launched only after an asteroid is found, but already waiting, prepared, maintained for years, ready to intercept a newly discovered threat long before it approaches Earth. Instead of beginning from scratch every time, humanity could possess a standing planetary defense system, almost like firefighters waiting before the alarm sounds. Some engineers imagine fleets of modular spacecraft capable of adapting to different situations. One mission might perform detailed reconnaissance. Another could deliver a kinetic impact. A third might accompany the asteroid for years as a gravitational tractor, each mission serving a different role, each designed long before it is ever needed. As our understanding grows, the strategies themselves will continue improving. The DART mission demonstrated that changing an asteroid's orbit is possible. Future missions will refine that knowledge. Scientists will better understand how different materials respond to impacts, how loose rubble behaves, how metallic asteroids differ from rocky ones. Every successful mission becomes another lesson, another piece of experience, another layer of confidence. One day, redirecting an asteroid may become a routine engineering task rather than a historic first. Perhaps the greatest transformation, however, will not be technological. It will be philosophical. For billions of years, Earth was simply another planet moving through space, its future shaped entirely by natural forces. Now, something unprecedented has appeared. Life has evolved to the point where it can understand the dangers surrounding its own world. not only understand them, but respond. This changes the relationship between a planet and its inhabitants. Earth is no longer merely home. It becomes something we actively protect. There is a quiet beauty in that idea. Every observatory, every spacecraft, every orbit calculated, every night spent searching the stars, represents an act of care, not for one nation, not for one generation, but for an entire world. Perhaps this is one of humanity's greatest achievements. Not because we have conquered nature. We have not. The universe remains unimaginably vast, powerful, and indifferent. Asteroids will continue traveling around the sun whether we exist or not. Gravity will continue shaping the solar system long after our civilization is gone. What has changed is something much smaller, and perhaps much more meaningful. We have learned to participate. Instead of simply witnessing the universe, we have begun interacting with it, carefully, respectfully, using knowledge rather than force. Imagine future children looking through telescopes 100 years from now. Perhaps they will grow up taking planetary defense for granted. Just as many people today rarely think about weather satellites or earthquake monitoring systems. The idea that humanity once lived without watching the sky may seem almost unimaginable. Perhaps they will inherit an Earth protected by generations of scientists they will never meet. Astronomers who spent countless quiet nights observing tiny points of light. Engineers who designed spacecraft capable of changing the paths of ancient rocks. Mathematicians who refined orbital calculations to extraordinary precision. Thousands of invisible contributions working together toward one shared purpose, protecting home. And maybe that is the greatest legacy planetary defense can offer. Not simply preventing disasters, but reminding humanity that cooperation itself is one of our strongest technologies. The universe often appears cold and silent, yet our response to it has become something profoundly human. We observe, we learn, we prepare, we protect. For the first time in Earth's history, a planet has developed guardians, not because the planet asked for them, but because one small species learned to care enough to become them. As our journey approaches its conclusion, only one question remains. After everything asteroids have done, after shaping planets, delivering water, changing the course of evolution, and inspiring humanity to protect its world, what does this entire story ultimately reveal about us? Our journey began billions of years ago, long before human beings existed, long before forests covered the continents, long before the first living cell emerged from Earth's ancient oceans. We followed small pieces of rock, drifting silently through space. At first, they seemed like little more than leftovers from the birth of the solar system. Ancient fragments, forgotten debris. But as we traveled together, a different picture slowly emerged. Asteroids were never merely rocks. They became part of Earth's story. They helped shape young worlds. They may have delivered water to our planet, perhaps even some of the ingredients that life itself required. Later, one enormous impact transformed the future of evolution. The age of the dinosaurs came to an end. The age of mammals slowly began. Eventually, human beings appeared. beneath the same sky. It is remarkable to think that our own existence may be connected, however indirectly, to one ancient asteroid that crossed Earth's path 66 million years ago. The universe has always shaped life in unexpected ways. For billions of years, Earth simply accepted whatever arrived from space. Every impact, every close encounter, every change in orbit occurred without warning, without preparation, without choice. Planets cannot look upward. They cannot calculate trajectories. They cannot imagine the future. But one day, something extraordinary happened. On one small world orbiting an ordinary star, life evolved into curiosity. Curiosity became knowledge. Knowledge became science. Science became understanding. And understanding became responsibility. That may be one of the most remarkable transformations in the history of our planet. For the first time, Earth possesses inhabitants capable of recognizing dangers long before they arrive. Not because they can control the universe. They cannot. Gravity still governs the motions of planets. Stars still live and die according to the laws of physics. Galaxies continue their slow dance across the cosmos. The universe remains wonderfully beyond our control. But within that vastness, a small species has discovered that understanding can sometimes accomplish what strength cannot. A gentle push, applied at precisely the right moment, can change the future. Perhaps there is a quiet lesson hidden inside that idea. So often, we imagine greatness as something dramatic, something loud, something overwhelming. Yet, planetary defense teaches the opposite. Sometimes, the greatest achievements begin with patient observation. A telescope collecting faint points of light, a scientist refining an equation, an engineer improving a spacecraft. Thousands of small acts, quietly combining into something extraordinary. The future is rarely changed by one spectacular moment alone. More often, it changes because countless people devote themselves to careful work that few will ever notice. Every night, while much of the world sleeps, astronomers continue watching the heavens. Most evenings bring nothing unusual, no dangerous asteroid, no historic discovery, just another peaceful night beneath the stars. And that is precisely the hope. Success in planetary defense is measured not by dramatic rescues, but by years of peaceful skies. There is another thought worth carrying with us. Throughout history, humanity has often dreamed of conquering nature, of mastering the forces surrounding us. But perhaps that was never the right goal. The universe is far too vast for conquest. Instead, we have learned something gentler. We can understand. We can prepare. We can cooperate. We can adapt. These qualities may prove far more valuable than domination ever could. Every successful planetary defense mission will ultimately represent a victory, not over nature, but alongside it, using the laws of physics rather than fighting them, listening to gravity rather than resisting it, learning from the universe rather than attempting to command it. Perhaps that is one of science's quiet forms of wisdom. It teaches us that understanding reality is often more powerful than trying to overpower it. There is also something deeply moving about the scale of this effort. Every telescope scanning the sky protects every nation. Every improved orbit calculation belongs to all of humanity. Asteroids do not recognize borders. The Earth they threaten is shared by everyone. In that sense, planetary defense may be one of the purest examples of global cooperation ever created. People separated by language, culture, politics, and geography work together because they all live beneath the same sky. Perhaps the universe has been teaching us this lesson from the beginning. From space, Earth has never appeared divided. The blue oceans flow without borders. The clouds drift freely across continents. The atmosphere belongs to no single country. Seen from far enough away, humanity has always been one family, sharing one remarkably fragile home. Maybe it takes looking outward to truly appreciate what we already have. Tonight, as you imagine another asteroid silently crossing the darkness between the planets, it may no longer seem like only a threat. It is also a reminder of where we came from, a reminder of how our world was shaped, a reminder that curiosity has become one of our greatest survival tools. Every asteroid carries the history of the solar system. Every observation carries hope for the future. There is no guarantee that humanity will prevent every cosmic danger. The universe will always surprise us. New challenges will appear. New discoveries will reshape what we believe possible. But perhaps certainty was never the goal. Preparedness is. Curiosity is. Responsibility is. For billions of years, Earth was simply another world drifting through space. Today, it is something quietly different. It is a world whose inhabitants have begun watching over it. That may not sound extraordinary at first, until we remember that, as far as we know, nowhere else in the universe have we yet discovered another planet doing the same. Perhaps there are countless civilizations protecting their own worlds. Perhaps we are the first. Perhaps we are one among many. We simply do not know. What we do know is that here, on this small blue planet, a species has learned to raise its eyes toward the stars, not only in wonder, but in care. The same curiosity that once asked what those tiny lights were, now calculates the paths of wandering worlds. The same imagination that invented stories about the heavens now builds spacecraft capable of gently changing the motion of celestial bodies. It is one of the quietest revolutions in human history, not because it happened suddenly, but because it happened gradually. One observation, one equation, one discovery at a time. So, could we stop an asteroid heading for Earth? Perhaps, if we discover it early enough. If we understand it well enough, if we work together wisely enough. Science suggests that the answer is increasingly becoming yes. But perhaps that is not the most remarkable conclusion. Perhaps the greater discovery is this. For the first time in Earth's 4.5 billion year history, one small species has become capable of understanding a threat arriving from the stars and trying to change its course. Before we learned how to protect the planet, we first learned how deeply it was worth protecting. And maybe that is the most beautiful journey of all. Good night.